Hello, this is a time series tutorial with R investigating stationarity of univariate time series. When stationarity can't be established, we look at methods to enforce stationarity-like conditions on time series. Some of the functions that we look at are outlined just below the title here. Here's a quick outline of what we're looking to achieve. Initially, we're just going to talk about some of the subjective judgment that's needed in working with time series and establishing stationarity. We're then going to go into some details looking at what the definition of stationarity is from a theoretical point of view, how that relates to real data, which has trend and seasonality, and modelling methodologies. From there, we'll move on to identifying stationary and non-stationary series, variance stabilising transformations that can be applied, other methods of dealing with non-stationarity such as differencing and time trend regression, and finally looking at ways to identify and remove seasonality from time series. As I mentioned, making time series stationary, it's more of an art than a science. A lot of it is based on using rules of thumb which are based on experience and backed up by theory, and often there's some creativity and intuition used with ideas of other models relating to methods to establish stationarity. Practically what you end up doing is fitting many stationary models and then choosing that which fits the data best, however also being the simplest explanation of the patterns being observed. I should also say that there are formal tests, but they are low power. They're low power in the sense that they have a very small beta, being the probability that a hypothesis is accepted given that its alternative is true. A time series xt is said to be weakly stationary or just stationary if for all t its expectation is constant with respect to time and its covariance depends only on lag rather than specific time points. So another way of seeing that is that on average the process stays constant and the covariance or the autocovariance between the process and itself at a lag depends only on the lag rather than the actual time. There's also strict stationarity, which is a probabilistic version of this, and it applies to higher moments. However, for modelling purposes, this is normally sufficient. Let's look at an example of a stationary process in R. We'll be using a package called TinR, which is a development environment, making it easier to read and write R scripts. And here's the R console. Okay, so I'll highlight the sections to be sent to R. Here we've just loaded up library mass and library T series. As an example of a stationary process, let's write in some white noise. Just simulations of 1,000 normals. And let's have a look at a plot of that. Okay. Now, as you can see, on average the process is staying around zero, mean, and it's the variance between processes, or the variance generally, is staying quite stable. So we're not seeing any bursty behaviour or differences in structure there. So that's an example of a very simple stationary process. The next thing to consider is that when we observe real data and more general time series, they tend to be such that they can be thought of in three parts. The first being a monotone, possibly stochastic trend, however usually deterministic, a periodic function that repeats itself after a period of time, and then a remainder process, which is the stationary process. So we're looking at a observed series composed of a monotone trend, a seasonal part, and then a stationary process. It's important to separate the monotone and seasonal parts. Certainly the monotone trend needs to be removed, and the seasonal function can sometimes be estimated simultaneously with the stationary process. It's very important not to attempt any modelling until you've established a level of stationarity. Let's create an example of this using R. Okay, so we'll have a time index first. That's just the numbers 1 to 500 used to index the time series. We'll look at a monotone trend, which is just a quadratic function. And we can plot that. As you can see here, we've got a quadratic monotone function. We can then look at a seasonal function coming from being composed of essentially a sine function that's been scaled. The last part of our example time series would be a stationary process. Without going into details, what we've composed here is a ARMA 2-1 process, and that's how it looks. Quite difficult to make anything out from that. Other than that, it does seem to be stationary. Again, judging that by constancy around the mean and a autocovariance structure that's not moving around so much. What we can now do is define an example time series being made up of the three parts: the monotone trend, the seasonal component, and the stationary process. Let's have a look at a plot of that. Okay, so looking at the plot, here we see the quadratic trend, the harmonic seasonal function, a stationary process which seems to have a structure about it. If we want to see it more clearly, we've got the actual series in black, a blue dotted line for the seasonal component plus the monotone trend, and a red broken line just for the monotone trend, just the quadratic part in that series. We can look at examples of real data too. So here I've taken some Barclays share price data and I've loaded that into R. I'll show you where I got that from. Okay, and this is Barclays share price data for today. It's up around 5%. And over a 5-year period, it's down roughly 80%. So to download that, I just go to historical prices, starting in 2004, updating the download and just taking it to a spreadsheet. Now coming back to R, let's have a look at how this series looks. So we see it's daily data with an opening price, a high for the day, a low, the closing price, and then the volume of shares sold in that day. What's the size of this? So it's just given as a matrix. It's 5 years of daily data, almost 1300 days, and 6 columns for the entries that we discussed. I'll just attach that now. I can confirm the names and the variables. Okay. Let's have a look at a plot of the time series of that. That's believable as a share price chart. However, the problem is it's in reverse. We're seeing today here and the past going forward in time, as it were. Let's reverse that. Let's define that. We can look at a plot of the price now. Okay, and that makes a lot more sense. So we had a steady increase for a few years and then a sharp decline over the past 2 years. I should say that we're skipping issues of holidays and weekends. It gets quite complicated to think about what the price is when the market's closed. We won't go into details about that, but we'll just take it as given from Google. Right, so we've seen an example time series that's non-stationary, and also a time series that from real data, which does seem to be non-stationary. Next, we need to think about which model to fit. It's really an iterative process where you try out many approaches until you find that model that's the most parsimonious from all of the adequate models that you've been able to pick out. It's also quite heuristic in the sense that there's not a strict procedure. You can screen many plots and fit many models before deciding on which to choose, and often you're flipping between your original assumptions and the final model that you reached at the end. Okay, now how do we tell if time series is not stationary? We've talked about the obvious idea of looking for a reflection around a mean.